a postdoctoral researcher at Caltech, also works with electrical stimulation, and wanting to know how we can convey information not just within the primary sensory cortex, but more in other brain regions outside of that, and how that can impact being able to better improve neuroprosthetics. All right.
I couldn't have said it any better. All right, awesome. And I also want to start by thanking the Polonium Foundation for having me. Everything has been awesome. The people have been awesome. The events have been really great, well organized. And the speakers, fantastic presentations. I'm really grateful to be a part of this. So thank you for the invitation. And then, so today I will be talking about my work on injecting information into the cortical reach to grasp network. And we do this with intracortical microstimulation. So right off the bat, you might have a few questions. The first being, what is the cortical reach to grasp network? So we can start there. I can maybe use. Awesome. So to begin, I want to focus on the primary output of the network and the primary input into the network. So the primary motor cortex is really the output, which controls movements of your body parts, and it has a few different representations for the face, for the hand and the arms, for the legs. And my work today will be focusing more on the hand and the arms and reaching and grasping. And the primary somatosensory cortex is the major source of input into this network. So that's your sense of touch, your tactile and proprioceptive information that's feeding into the network. And the next two regions I want to focus on are starting to get into these more complex association cortical regions. So that's the dorsal premotor cortex and the dorsal posterior parietal cortex. And both of these regions are largely implicated in reaching movements. So things like integrating partial pieces of motor information to generate reaches, or integrating visual information to reach towards targets. And then there's two additional regions I want to focus on today, and that's the ventral premotor cortex and the anterior intraparietal area. So these are more of the grasping regions, so when you're actually going to pick up objects, and they focus on things like shaping your hand according to the shape of the object or transforming properties about those objects into the proper motor commands. And the beginning of my talk today will focus on monkeys, so that's why I'm showing a rhesus macaque brain. But I also eventually will transition to work in humans, so I just wanted to show that these areas do have homologs in the human brain as well. And so you can appreciate kind of the difference in size and how it's evolved from the monkey into the human. The second question you might be wondering is, what is intracortical microstimulation? So just breaking down those words into their components, we have intra meaning within, and cortex meaning or cortical meaning the cortex, right, the surface of the brain where a lot of these neurons are located. And then we're delivering micro stimulation. So that is just small, and in this case, electrical current pulses. And if we zoom in on the surface of the brain here, you can see that we can get down to the level of individual neurons where we're sticking these electrodes. In this case, I'll show you arrays that each have 64 different electrodes on it. But you can imagine if you were to deliver small current pulses, you can then cause the neuron to fire action potentials. And these action potentials are how the neurons communicate with each other. So if we can causally drive them to fire these action potentials, we can then also communicate with the brain. And you can vary the shape of the stimulation in many different ways. You can change the amplitude, making it stronger or weaker, the frequency, how close in time these pulses come together, and the duration, how many pulses we're delivering. And if you vary all these parameters, you can excite the neurons in different ways to evoke or deliver different kinds of information. So next I want to talk about how these things are really used in the context of brain-machine interfaces. So if we're starting with the brain and we want to use those brain signals to control a prosthetic hand or arm per se, you could imagine sticking one of these arrays. They're 2 millimeters by 2 millimeters in size, but you can stick them into the cortex and record neural signals from each of those electrodes. And you can feed that information into a signal processor and eventually a computer and extract features of that information to drive a prosthetic hand. And so that's why the primary motor cortex is a good place to start, as it's the major source of output from this network. You might also then take information about the prosthetic hand, feed it back to the computer, use that to drive a neural stimulator, and then interface with the primary source of input into the network, that somatosensory cortex, and you can deliver information about the prosthetic hands back to the brain and restore things like the sense of touch. And finally, the current state of the art of these brain-machine interfaces are to start to move to these more advanced regions where you can now decode additional information to control more complicated movements with fewer numbers of neurons. And so I want to show a few example studies of how this has been done. So I want to start, this one was performed at the University of Pittsburgh. They have a human participant implanted in both motor and primary sensory cortex. And if we look at the figures on the right, you can see these box plots focusing on the ones in gray are when we're just decoding, or they were just decoding from primary motor cortex. And they were able to achieve grasping movements, reaching movements, transporting objects. But you might also notice that the time it takes to do some of these things are a little bit longer than natural movements. So if I was to reach and grab something, it might not quite take 25 seconds. When you now introduce sensory feedback through the stimulation, you can see how much better you immediately can do by adding in that sensory information. So when they delivered the stimulation to the humans, things dramatically improved. But even though they're much better, it's really cool, really impressive that they can do this, it's still not quite as good as natural movements. So we want to continue trying to improve these brain-machine interfaces. This is a recent study from our lab that was published a few years ago, just before I got there, where they implanted some parietal cortical regions where single neurons cared about things like entire reach trajectories or even specific actions like reaching towards your mouth versus your cheek. So you could imagine how having access to these neurons might improve these devices. And I want to play a little video so you can see exactly how this device works. They have a target on the screen. And as soon as they move the target, the participant can just think and imagine moving towards the different targets, and you can decode that information to track things pretty quickly. It performs really well. So this is the current state of the art, and now I want to get more into my research of how we want to push these things even further to the next level. So the next logical question I saw when looking at this diagram was, can we also deliver more complex information by stimulating those regions beyond the primary sensory cortex? And this began when I was in graduate school doing my PhD work, where we worked with monkeys. And this was a really big challenge because as much as I wanted to, I couldn't speak to the monkeys. I couldn't ask them to do certain things. So we had to get really creative and figure out a way to ask the monkeys without English if they were perceiving the stimulation. And the way we decided to do that, first we defined the idea of injecting information altogether, which would be to elicit distinguishable experiences with the information. So by that, I mean an experience or a percept, a thought, an urge, a desire. We don't know exactly what it's going to be, but an experience. And then we also needed different experiences to be different from each other or distinguishable. And so to do that, we trained the monkeys to do this center out target task, where they would move a cursor using a joystick to the center of a ring of targets. We would then instruct one of the targets they were supposed to reach toward using brain stimulation. And if they moved the cursor to the correct target and held it there, they received a reward. And if they could successfully do this, it taught us two very important things. The first, if they knew when to leave that center and go towards a target, they must be experiencing something caused by the stimulation. And if they knew which of the four targets to move toward, the different experiences by different instructions were also distinguishable. So we were saying this was sufficient to conclude that we could elicit distinguishable experiences, and these might be good areas to study in humans for brain-machine interfaces and delivering information. So I also have a video of, I'm a very proud man of my monkey here, doing this task successfully with brain stimulation. You can see all of these targets remain the same color, and we have no idea which ones are instructed, but the monkey knows exactly where to move the cursor in a very fast time frame. So just shout out to him for being an awesome participant. And we tested this in all of the regions that I outlined at the beginning of the talk, finding interestingly, well, unsurprisingly, you could do this in S1, where this has been done before, but also you can do this with both of the grasp regions of that ventral stream. However, the monkeys were not able to learn this in the dorsal stream related to reaching, and this was consistent across two monkeys. And even more interesting and surprising to us was when we varied the parameters, such as amplitude, frequency, and duration, and we looked at how the monkey's performance changed. There was very similar sensitivity among all of these regions. So even though the primary sensory cortex is the first source of input into the network, when you stimulate some of these higher regions, the stimulation can be appreciated at very remarkably similar levels. So then I was fortunate enough after my graduate school to go to a lab over at Caltech where they have humans implanted in these regions and also FDA approval to deliver stimulation. So now I could finally ask those questions about what these experiences were like. But even that, asking humans is not quite as straightforward as you might think. So right now, if I was to ask the audience, are you perceiving anything in your body, right? You might have a caffeine rush from the coffee. You might have an itch on your arm. You might have the urge to talk about Poland. But I'm not delivering any stimulation to any of you right now. So you can't say that it was caused by the stimulation. That might be these experiences that overlap in time but aren't caused by the stimulation. So how do we navigate through these weeds? Well, we delivered stimulation in a two-alternative forced choice paradigm. We represented two identical periods in which stimulation might be delivered, but we only actually stimulate during one of them. And then we ask the participant to choose which one contained a stimulation train. And if they can correctly identify the period many, many times, we can build confidence that there is an experience that's being causally produced by the stimulation. And so we did this for all of the electrodes implanted in a focus on AIP right now. And we would repeat it 5 times, and after 5 repetitions, randomly shuffling the channels, we would collect detailed reports so we could learn about the types of experiences they had. And if they had consistently correct choices, we could then say these are the experiences that were caused by that stimulation. And so here I have a few examples of some data that we collected. So we repeated each set of 5 twice for the electrodes. Along the y-axis are just different example electrodes. The green circles mean that the particular choice was correct. Red X's mean that they were not correct. The black dots mean that they did report a detailed experience, but sometimes they didn't. And on the right here is the confidence in each of those choices. So a few interesting things to note. For some electrodes, like 165, the first time we did this, they got it wrong many times and reported no experience. But the second time we tried it, they got it correct all 5 times and reported an experience. If we look at electrode 188, sometimes there was no experiences and sometimes they were randomly correct or not. In other choices, like 200 or electrodes, like 200 through 205, they were consistently correct, always reported experiences, had high confidence, so these were kind of our star channels. And even in some interesting cases, like 168, the participant was correct all 10 times, but never reported an experience, which we thought was very interesting. So I'll be curious to study that channel more. And now the most interesting part, in my opinion, is what were the actual reports of the experiences. So here's an example of electrode 165. He said this was not at all like a sensory percept. He said it was instead like suddenly experiencing a different state of awareness about that area in the hand, which it's really difficult for them to explain these experiences that aren't necessarily intuitive, or maybe they never had before. You could imagine trying to, the classic example of somebody who was blind, if you were trying to explain the color red to them. That's a very big challenge because they've never really seen the color red before. So keep that in mind as you listen to some of these descriptions. Another one here, this was more of a feeling of intention, but I can't determine the action. So more of an intention to feel something than to move. That was electrode 178. And one of our, I think this is why he had higher confidence, is a more familiar experience. He described this one more as a sensory experience. So it was a jab with something sharp, intense but not painful. It was more like with a screwdriver than a pinprick. So just really interesting, diverse experiences. And so the next step we wanted to take was actually quantifying what these experiences were like and how many electrodes they occurred on. So here is a histogram summarizing for each of the channels how many choices were correct. And on 41 out of 64 channels we tested, which is 64%, they all had greater than or equal to 9 correct choices. And that is an important number because according to a binomial distribution with a 50% chance of being correct, guessing 9 or more correct occurs less than 5% of the time. So we use this as an important indicator of significance. So lots of channels with reliable experiences. He reported all of them to be localized to the hand, which is important because that's the network we were targeting to control these brain-machine interfaces. And interestingly, being on the pinky, the ring finger, and the side of the hand, this was the most insensate region of his hand. So this is also a patient with tetraplegia with some residual sensation, but this was the most insensate part. So really cool that we can still get experiences located to that part of the hand. They also had some organized somatotopy. So if we look at these implanted arrays, you can see a diagram of the central sulcus, the intraparietal sulcus, where we have these sensory cortex arrays, and also the AIP array. In sensory cortex, there's very, very strict organization, as has been studied and discovered before, where one array had lots of locations reported on the thumb. The other array toggled between the index and middle finger with pretty drastic lines showing which were which. When you get to the anterior intraparietal area, there is some organization where the upper left corner is more located on the palm, moving towards the pinky and other fingers towards the other side of the array. But what's also interesting is it's a little bit more intermixed and complicated. And that's what you actually might expect if this truly is higher up the cortical hierarchy and the processing in S1 is being projected to this area. It's going to start combining things and integrating them. And finally, we looked at detection thresholds for the stimulation. So I'm reporting that for the amplitudes here, detection thresholds were as low as 9 microamps, which is a really, really low level of stimulation. Arguably the same, if not lower, than some of the channels in S1. So really cool to see, again, in humans, very similar detection thresholds that are kind of organized to those channels in the left half of the array. So finally, just to summarize, I want to point out that starting in monkeys, the stimulation was appreciated in the ventral but not dorsal streams of this cortical reach to grass network. In humans, the ICMS delivered an AIP elicited experiences that had similar detection thresholds to the primary somatosensory cortex. And while both had experiences that were located on the hands, their qualias were distinct. So you might imagine delivering different types of information to both cortical regions to improve control over these brain-machine interfaces. And of course, lots of interesting future questions. The first one that's immediately obvious, what happens when we study some of these other regions? We're going to continue working with some of the other areas we have implanted. You might also imagine what information can be decoded from electrodes and delivered to the same electrodes that are now interfacing with neurons that are located in the immediate spatial vicinity of the electrode, so they're going to care about the same areas on the hands. And what my current research is really geared towards that I'm super interested in is studying the neuromodulation that's produced by the stimulation that we can now study across an entire network and maybe correlate some of these neural underpinnings of the behavioral experiences. And so with all of that, of course, it takes a village to do these things, starting at the University of Rochester, now moving to Caltech. And most importantly are the participants, the human participants I work with that give an extraordinary amount of time and dedication to this work to help me get these results. So thank you.